Very good. Good. Chalo, so let's see where we were last time. We'll have to review things quickly. Okay, good. So we were doing, we started with Salav's right? And essentially, as we said, the intuition is that you have ln y. This is the empirical distribution of ID samples y1 through yn, which are in a finite alphabet, them lying in some set gamma, and then we did large deviation of that. But roughly, we said that this, I think, I'm saying this. Looking like nu, for nu corresponds to values the empirical distribution can take. This looks like e to the power minus nh n nu. So that's the first order intuition, right? Everything follows from that. Right. So now we are again given the same alphabet A1, A2. But now we have a function which is mapping sigma to ln, and we have y1, y2, and so on. I with distribution mu on sigma. Right, that's what we have. And then we said, okay, then we said, let's look at Sn by n, which is equal to summation Fyi I equal to 1 to n 1 by n, and that's same as the scalar product of f and ln 1. Okay. And now we want to talk about large deviation of this guy, and that's conventional. And the theorem that we started proving last time, probably have it here. And let's just follow it. Let me see if I remember it correctly, what it was. Probability that Sn by n lies in set A. So we said, okay, let's collect all the gammas so that f n by f nu, I guess. That's set A, right? And let's call this set as gamma. Right. So Sn by n lying in A same as nu lying in ln y lying in sigma. A is it's basically the subset of I'm going to assume, for example, that FA1 is less than FA2. This is a process value. F G last value, and then we'll assume that K is equal to F1 FA. So A is a subset of A. Because Sn by n is lying in this set. I could keep with bigger, but don't gain much.
Any measurable subset.
Any measurable subset. It's all finite, so what does it mean? Okay, and even later when we do, we worry about open sets and closed sets. And we won't talk about measurable sets so far. Okay, so we are talking about this, and the theorem was that okay, then inf as n goes to infinity, probability Sn by n in A is of course is rather equal to then soup as n goes to infinity, probability Sn by n in A, and that's going to be that's equal to minus infimum h mu mu that we know where now you have mu like it's at gamma, right? But this is equal to minus infimum I of x I set. Because that was the result we saw. When we define I of x in this pattern, this is going to be minus infimum h mu lies in gamma naught, and that's equal to minus infimum x lies in a naught, where I of x is equal to infimum h mu, where f. So this infimum of all mu such that f mu the dot product is equal to x. Okay. It's like all the different distributions that can achieve mean of x. We look at the one which has the smallest rate function, most likely, which is closest to mu. And that's going to be the one that it. So basically what you're saying is that Sn by n, just like L and Y sequence was satisfying a large rate function. Yeah, there must be log somewhere. Log and
1 by
log. Okay. Yeah. By n log. Right. What was I going to say? Yeah, so just like L and Y sequence satisfies the large division principle with rate function h nu mu equal by Glavier distance, Sn by n satisfies the large division principle on the real line with rate function I.
What is A0?
A0 is your open set, right? Yeah. Interior of A. That was gamma 0, that was interior of gamma. And I of x is equal to soup lambda x minus lambda for all x in k. It is continuous in k. Lambda is the log. Right. This is log moving function. Okay. So this was the result that we had to show last time. The way we started was we said that yeah, I guess we use Jensen's on this, right? Log of summation pi equal to 1 to sigma. That's right, it's a mu of AI upon mu of AI. By lambda f AI. mu of A. Now it's an expectation under measure mu of this random variable, right? And this is going to be dominated by summation I equal to 1 to sigma, and then you have log inside mu of AI, mu of AI, e to the power lambda f of A. Right. And then we said that this simplifies to, we check it, we did it last time, this is equal to f mu lambda lambda mu minus h mu. ठीक है. This is now useful. In particular, we had said that okay, this was just an aside. This gives you this duality that supremum over nu lambda f mu. This is equality. And we saw this by considering nu, which was mu but exponentially twisted by lambda. Because that's all very nice. But where we are going with this is now we have h mu mu. Right? Basically, what do we need to show to prove that theorem? We need to show, so we define I of x to be equal to infimum h mu mu. Then we said f mu is equal to x. Okay. Right. Right. So as such, yeah, so with that, of course, from Sarno's theorem, the first step follows. F nu is equal to x. X is an A. Right? So we're just re-expressing this as this. They're obviously equal. F h nu mu, no. H nu mu where nu lies in gamma is same as infimum of h nu mu, mu lies in gamma, same as infimum of I of x, x lying in A. When we define I of x to be infimum of h nu mu, such that mean under mu is equal to x. So that part is true. So all we really need to show is this thing right here. We need to show that this quantity here is equal to this quantity here. And then I of x is continuous. That's what we really need to show. So how do we show that?
Keep the formula for gamma. They needed that formula.
Gamma is just mu, so the f nu is in A, right?
No, the delta of gamma.
This
Yes, and
big lambda of small
yes,
lambda.
yes.
This is right here. The log homogeneous function. You should get friendly with this, huh? People just log homogeneous function are usually called by big lambda. But it's just a very important quantity for any lambda variable. It's also called cumulative function. Okay, so all right, so we have to show basically that I of x is given by infimum h nu mu is given by supremum of that thing for all x in k. That's all. So now from our duality we have h nu mu is greater than or equal to lambda f nu minus big lambda square. Okay. So in particular, it follows from here that infimum nu such that f nu is equal to x h nu mu is less than or equal to minimum lambda lambda x minus okay. Sujata, you're okay with this thing here? Yes. Okay. So now what we'll do is so we look at these twisted distributions, right? Mu lambda ai is equal to mu ai e to power lambda fai minus normalized by big lambda small lambda. Okay. So when by varying lambda from plus infinity from minus infinity to plus infinity, we can get through this distribution f nu. That's just the mean that we are achieving, right? And it's the mean of f under this distribution. That's what this means actually. Yeah. Probably should have called it that. We can achieve mean from minus fai, basically in the k of interior of k we can achieve. Minimum to maximum. But not the last ones. Yeah. Because we are assuming in all of this, okay, we are maintaining absolute continuity. In the sense, even lambda is not is always a real number. It's not minus infinity or plus infinity. So for real numbers, you can get arbitrarily close. So Sunanda, are you up to date on this? Because we said that under mu lambda, what is the mean under this distribution? So what is f mu lambda? This is going to be summation f ai mu ai bar lambda f ai. Right, and that's equal to lambda prime. Okay, this part is clear. Right. But staring at this, you can see that if I take lambda to be minus infinity, as close to minus, I move towards minus infinity. I'm putting all my mass at fa1. If I take it to plus infinity, I'm putting all my mass at
A sigma.
fa sigma. Yeah. So basically, this lambda prime lambda, as lambda goes from minus infinity to plus infinity, it takes values in k naught. If I just collect lambda, so if I collect this guy, so that lambda lies in R, I get k. Take it this way. Right. So now so what I'll show is, so let me take one such lambda here. So f nu lambda is equal to x. I can do this for x lying in this set in k naught. For x lying in k naught, I can always find a lambda. So that f nu lambda is equal to x. Okay. Now for that lambda, let's evaluate both of those. Let's evaluate lambda x minus lambda, and let's also evaluate h nu lambda mu. And let me evaluate this guy. Okay, so this is what is this? This is going to be summation nu lambda ai log of nu lambda ai by mu I, right? And that's just going to be equal to e to the power lambda fai big lambda small lambda. Right? Okay, so now what happens? So let's so lambda times f in new lambda.
So what is this expression? This is what?
This is what this gets,
Oh,
right? All the probabilities, log or ratio probabilities. No magic. But now you know if you see this log e of this guy, that's at lambda of FAI, right? That will sum with this guy. So that gives you basically x, lambda times x. Minus okay. So yeah. So basically at new lambda, we have defined x as follows. I get that these two are equal. So basically I get that okay, in that case, for such x I have I of x equal to infimum. Yeah, two sides are equal. So infimum of 1 is equal to the yeah. So I've established what I want to establish for all such x. Okay.
so what here we assume this thing such a so we came to f lambda to there. So how do we need a continuity?
So continuity of what?
So we said that this such a
X exists.
yeah like for any
Okay, so
lambda there is
yeah. So your point is, if I collected all these lambda prime, if I have collected all the lambda, I've taken lambda from minus infinity plus infinity, and I've collected all the lambda prime lambda. How did I get an interval?
yeah. So we said that take any x there and there exists.
Yeah. Yeah. So we've also shown that lambda prime lambda is strictly increasing. So because we showed that this double derivative was convex, is constant. Last time we showed that, right? Yeah. That's true. So that has to be taken into account.
But also like derivatives satisfy that internal.
Yeah. This is a differential function.
Yeah.
So it's also continuous. Yeah.
Okay.
We differentiated this last time.
Uh,
So yeah, that's important to mention on that. So hence it's a proper interval that you get from FA1 to FA right. So for any x, now we've shown this equality. Okay. I guess I should probably show that Ix is continuous. The point was, the argument of course is that Ix is equal to infimum h nu mu if mu is equal to x, and this guarantees that this must be continuous.
Isn't the integral of any family of continuous function?
That is not good.
But wait, this is fine.
Yeah, so it requires special properties. So I don't recall them exactly right now. That So what? So I don't know. Maybe you can come with examples more quickly. Where are the cases where this might be discontinuous? I mean, generically speaking, and how are we? Does finiteness ensure continuity, or is it something else? Or is it just the fact that this? First of all, this is a continuous function of mu, right? Now, of course, one can actually differentiate this. One can just write the form of this, put this as a constraint, come up with Lagrangian near to the optimization, and then you'll actually see that what will solve this is the new lambda distribution, where lambda is such that okay, you have lambda prime and small lambda equal to x. So now what does that mean now? So right now I don't see an easy proof for this. So this would be equal to. So let's call this as lambda x. This equation has a unique solution lambda, right? This is a strictly increasing function. So it has a nice unique solution here. And then this is exactly equal to h of nu lambda x and mu. Just you can minimize this and see. This is not so difficult. This is calculus. So now the question is, how is this a continuous function of x? So that would require lambda x to be a continuous function of x. So right now the only proof I have is that okay, you can apply implicit function theorem to this. Are you familiar with implicit function theorem or? No. So then you'll get that lambda x is a continuous
So
function.
it is only derivative.
Its derivative, it's positive, the derivative is positive. Strictly convex, right?
Inverse function.
Yeah.
Inverse function.
Inverse function. No, inverse function theorem is. I mean, this lambda is an implicit function of x. So it's more an implicit function theorem. Yeah. But yeah, I mean, there are two are related, I guess. So I'm implicitly defining this function here. For every x, I get a different lambda x. But since lambda prime is differentiable, this lambda x will also be a nice differentiable. So it will be a continuous function. So this will be continuous. Then there should be an easy argument. I just don't remember it right now. The book, I think, when I was reading it, was kind of dismissive of this. So I kind of also didn't think much about it. But this will certainly work. Or you can also maybe come from here, because we have established this equality, right? And again, now when you evaluate this, this is going to be, again, it's going to be lambda x minus lambda x. Because this is now, okay, strict concave function. And we know we have a concave function and we know a point where its derivative is 0. So that is the point at which the maximum is achieved. And if I give you a concave function, and if I tell you at this point its derivative is 0, then that has to be global optimum. Then you don't have to worry, you've got a global optimum. So it will be lambda x minus lambda x. And now again from here lambda x is continuous. So this will be continuous. So this is slightly okay, you know, I have to rely on differentiability and all these things.
So complexity just corresponds like that increases to p1 over
Convexity of this follows. Yeah, that's right. That's true. Convexity of I of x follows from that. Yeah.
Yeah, so p1 of any time.
True. This is no, hold on. This I think it's concave.
Concave.
Yeah, okay.
Yeah. So. Okay, hold on. So any x I have a maximum. So it is a concave function of x, right? Yeah, I mean right now I'm just saying that because no, that's why I never doubted the fact that it was not concave. So it is concave, sure. It is a concave function, and hence if I show you one point at which its derivative is 0, I guess I was just talking about this function. Yeah. So I'm not really talking about I of x. I of x is fixed for me. X is fixed for me right now. So I'm talking about this function, and this is also concave. Right? And this function has a unique point at which the derivative is equal to 0. So that must be the maximum. And that corresponds to this equation. So we know this equation has a solution. So hence this has a unique point. So solution hence this is equal to lambda x minus lambda x. Right? I mean, all I've said is if I give you convex function, if I tell you at one point derivative is 0, then that must be the point of maximum. Now I know this function is differentiable, its derivative is 0 at lambda x. So lambda x must be maximum. At that point, the value is lambda x minus lambda x. Now we look at this as a function of x. Here it's a continuous function, right? Because lambda x itself is a function of x. This is a slightly more involved argument. There are nicer arguments for these things to show continuity enough. But it's good to know this also, I guess. Yeah. Okay. Is that okay, Malhar, Saurabh?
Yes, sir.
Yeah. Okay. Not seeing your faces anymore. Okay, so we got this now, right? Where are we? Yeah, so we established that I of x is equal to this, and I of x is continuous in the interior of K naught. Okay, so all we really need to now show is that I of x is continuous even at the boundaries. That the property of the definition of I of x holds even at the boundary.
The real piece argument is
What's that?
this invert function failure who gave it to open set.
Yeah. Just the open set.
So can we extend the definition?
Oh, you mean to the boundary?
I mean, open set.
I mean, one just will have to be very careful, I guess, with the few things you're doing, because your nu and mu will no longer be absolutely continuous at the boundary. Right? Nu will be giving all the mass at FA1. So one just has to be careful to make sure that everywhere things are going smoothly. So presumably, I would imagine yes, but you'll have to take care, etc. But now I'll just give you one argument which is kind of somewhat similar. This, let me see. So we'll take new star, so the new star A1 is equal to 1 and 0 elsewhere. Then we have H mu star mu, right? And this is equal to log of mu of A1 minus, and mu star A1 is 1, log of 1 upon mu A1 plus 0 everywhere else. Because this we get from here. This is greater than equal to I of, I guess I'm between A1 and F of A1, right? Yeah. So F mu star is equal to F of A1. So I of F of A1. Let me call this as X. I of X. And I already know that this is greater than equal to. So from duality. For the duality, I didn't really need any absolute duality. So lambda x minus greater than 4. Any lambda? Let's just write this down. This is equal to. This is log. I think this is log. Summation mu ai, right? U bar lambda FA. Okay. Now my x is nothing but FA1, right? So I can just write this as now you can see that as lambda goes to minus infinity, minus 2 log of mu of a. Right. So this f of a1 is not there. Everywhere else, this is going to 0. Okay. So this quantity is turned into log of mu of a1. Is there a minus somewhere or is it? Yeah. Oh yeah. So where is the minus coming in? Yeah, this was always a minus, I guess. Right? Yeah. There's a minus here.
Definition of
So it's
Well, I mean, I just took it. Yeah, I just lambda of FA1, x equal to FA1 minus. And this is equal to this, right? Yeah, it's yeah. So you get that. So then this is equal to this, basically, right? So hence, yeah, this is equal to this. So you can continue. So even at x equal to FA1, I of x equal to this quantity right here. think you probably need slightly more argument to say that okay, I of SA1 plus epsilon is converting to minus log of mu. So that's some argument is the as epsilon goes to 0. So you can just take it for granted that it's true. I'm not sure this. So we get that I of x is continuous. Don't want to spend too much time on this particular aspect. It's a technicality one can verify offline. We've shown I of x is continuous in K naught. We've shown its value in the corners. We've not shown that the value equals a limit. That we can show. But let's move on now to full-blown Cremers theorem. Now on a proper distribution of real line, arbitrary distribution of real line. Cremers theorem.
The previous theorem was this Sanos theorem.
Yeah, it was just on finite alphabet. So from Sanos theorem, Cremers theorem followed basically. And then we were simply checking that I of x rate function has two different definitions, which are the same thing. So that's kind of application of contraction principle to, so Sn by n was kind of a continuous function of the underlying distribution, right? Of the underlying empirical distribution. So that idea generalizes that if I find a large deviation principle for the some sequence of random variables, then their continuous functions will also satisfy a large deviation principle. So that was one illustration of that idea. But now we'll prove Cremers theorem more generally on the real line, and we use different tools and techniques for it. More like change of measure kind of arguments. But let me just say a few before I do this. Let me just say a few generic things. So I've been using this, but let me just say it once formally. So sequence of probability measure need not be a sequence, could be a direction. Mu epsilon is set to satisfy the large deviations principle this is on a on a topological is x with function I, which is mapping x to 0 to infinity. if gamma in V of x. So this is the Borel sigma algebra corresponding to the topological space. So I should say there's a topological space, there's a collection of open sets, and there's a Borel sigma algebra corresponding to open sets. We have something I'm missing. If then no, let me just see. I get that complete the statement. If we have the usual stuff. Let's get against the next one. So this is a more abstract statement of the large deviation. We need some more qualification.
That gamma binds closure. Gamma is closure of
Yeah. A rate function I is a lower semi continuous. So you know what I mean by lower semi-continuous function, right?
the lower limit exists.
The lower limit exists. Another thing is that the level sets are closed. If I psi I alpha x, then I of x is less than equal to alpha. Then closed. That's what I mean by lower semi-continuity, that the level sets are closed. Now, if the level sets are also compact, then I say it's a good rate function. So essentially, where am I going with this? In Gamer's theorem, what I'll argue right now is
Can you repeat the argument about compactness that you have given?
So what's the point?
What did you say about compactness?
Why is there compactness? Sorry, is that the question?
Yeah.
No, I think if they are compact.
Okay.
See, these guys have to be closed for I to be a rate function.
Yes.
But if they're also compact, then we say it's a good rate function. It need not be true.
Okay.
Right? When phi I alpha is compact for each alpha, we say that phi is a good rate function. I guess the point is, so let me try and see. So typically, we expect weight function in commit setting, there'll be some mean of the underlying distribution. And we'd expect the rate function there to be 0. Something like this. This is the large rate function, the I of x that we saw. So it's a good rate function if whenever I draw any level, it's going to plus infinity on both sides. Like typically it's going to be a convex function in our setting, in the IID setting. Need not always be convex, by the way. I'll give you some examples later when the rate function is. It's going to be quasi-convex in the sense it's always going to be non-decreasing on this side of mean and non-increasing on this side of mean, but need not be convex. But for IID distribution, it will always be convex. Now the level set is, this is a nice thing because it's going to plus infinity basically. Right? Now you could also have settings where, it could be here and then it becomes plus infinity. Which is some point here and becomes plus infinity. So we'll see examples of this. This is, for example, if we have bounded random variables, right? The chance of this event happening as average coming here is 0. So those things are, it's not uncommon at all for these things to happen. So then also the level sets are going to be compact. Okay. So typically you will see a good rate function. Where you don't see a good rate function is where it's always equal to 0. That's going to happen when you have heavy tail random variables. Then the rare events have polynomial tail probabilities. So on a logarithmic, on exponential scale, it's they don't show up. So it's quite large probability everywhere. So it's the rate function in that case will be 0. We'll see that in a moment. In that case, you don't have a good rate function. But if you take it for granted, let me see if I can show an example that So when we're going with this, we want to say that Sn by n close to small x looks like e bar minus nix. That's the intuitive content of large initial function, right? So Ix is then measuring the rarity of Sn by n taking this value x. Now if I give you, let's say S of n t by n of t, which is equal to summation xi n of t, 1 t, let's say. So now the number of terms itself becomes random. So this is when n is fixed here, right? Sn by n is just summation xi I equal to 1 to n upon 1 by n. Okay. But now suppose I give you S of n of t upon n of t.
N of t is stopping time.
N of t is the stopping time, counting time. For example, n of t can be a Poisson process. Okay. So n of t can be soup n, so that's some other summation tau I equal to 1 to n is less or equal to t. Tau I is the ID, for example. It's like you incur so much cost, so much. I don't know what language to give you right now. It doesn't come to me. But after tau I time, you get a reward of xi. Then another tau j time, you get another reward, so on and so forth. And then you say, okay, does this guy satisfy a large diffusion principle as t goes to infinity? I'm just giving you an example. What could also happen is that so one way the rare event will happen is because n of t takes. So suppose n of t has a value of which is linearly increasing with t, like a Poisson process, it's some lambda times t. Okay. So one way this can take a rare event is that n of t looks like lambda t. So the number of terms is going to infinity, but this summation xi takes a large deviation. But what could also happen is that n of t itself takes a very small value. The summation tau i's take a large value, so n of t is small, right? Because some tau i's took a large value, and then this guy took a with deviation above x. That becomes very easy. If there are only 5 terms, for average of 5 terms to go beyond some large value is very easy to happen. So then how the rate event happens depends on 2 different phenomena. One is tau I is taking large values, other is and for if tau I is exponentially distributed, probability that tau I is greater than equal to t is e to the power minus lambda t. On exponential scaling, it has some rate lambda. So what happens here is this. Let me just say a quick point here. We'll come back to this maybe later. But in this case, if you were to find the large deviation rate function of this quantity, that would look like this. Meaning no matter how far you are, it's not that rare to get there. Because you can always have an event where tau 1 was very large. So you had only one sample, and then one sample can take any value with positive probability. So for the sample average to look like it's 2000 or 200,000, they're all kind of equally rare. It all depends on whether you see one tau plane. Tau plane is this is x here, this is I of x, and this is probably I x, e to the minus n. This is going to be lambda. Because with probability e to the minus lambda t, you see either n of t is equal to 0 or 1 or 2, all of them are essentially with probability e to the minus lambda t with some small corrections. So you get these kind of behaviors. So I just want to give you an example that it's not uncommon to see large deviation rate functions, which need not go to plus infinity. And there's very good intuition for them because there are other factors which are determining how the rate happens. But it's a nice example. I don't know if you can appreciate it, but SNT1 NFT. If you do so much of large deviation theory, and you never expect to see rate functions which are funny looking, and you find it comes so simply and with very clear intuition. But you can see in abstractly, this sequence will satisfy the large deviation principle. You can identify the rate function as this sequence. Okay. So let's carry on. Yeah, so we define the good rate function. Now we just want to commit, right?
What was the previous statement that if large deviation holds for finite times, then it also holds for all stopping times?
No. I mean, this was a very hand-wavy argument.
No.
But all I was saying was that you can imagine this sequence now. This sequence is inducing a distribution on real line for each t. So now that sequence of random variables, let's call it xt, is satisfying the large division, and distribution corresponding to is p of t is satisfying the large division principle, and that will have a rate function on the real line, and the rate function will no longer be convex.
Oh,
That's all I'm saying. It will still be 0 at the mean of
but it will
xi.
still satisfy large deviation.
That's right. It will still satisfy all the purposes of calculation. Yeah. So that was, maybe it was too early to mention this. I should explain the commits first, but in any case, I think it's fair. But that's a nice thing of large division theory that you can imagine all kinds of funky things and prove large division principle for them. And then, once you can show that they satisfy the large division principle, you can say a lot more on top of that, like contraction principle, that continuous function of these guys also satisfy large division principle with the rate function that's easy to identify. So that was the kind of contribution of Varadhan, that he axiomatized all of this. He said, okay, if something satisfies the large division principle, then they also satisfy what's called Varadhan's integral lemma and contraction theorem, all of these things. So a lot of kind of things in great generality were said in his framework. So Varadhan, I don't know if you know, he got Abel Prize primarily for his work on this stuff. But lots of things, but this was the main work. Okay, so Premier's theorem. Okay, it says here go and have tea quickly. So we'll have that right now. So guys, shall we just meet at maybe 4:12 or something? 4:12 or something? And we'll go on till around 5, maybe 5 or 5. Okay. Anyone you want to come? We can have a 5-minute chat while we're at it. Let's make this tea time also. तो आना चाहती
हाँ सर
साइन करा हुआ तो हाँ वही लैम्डा टी से बड़ा उसको
So Sunanda, are you lost right now or are you following? So sorry, you were supposed to close the recording, but I think recording continued. I guess the break went longer than anticipated. So we'll start immediately with this. Where's Shantanu? He's not around.
He's feeling.
Hmm?
He's feeling. He's not feeling.
He's not feeling. Yeah, I guess the videos are there. So. Okay. So we're going to. So the theorem just follows. So you just take the theorem. Before that, let's just define lambda star x. And you know what we had earlier. So lambda x minus 3 lambda 1. So this is called Fenchel-Legendre transform of this function. So lambda star x. So basically, you know, if you know this is a convex function, right? Maybe something like this. It is strictly increasing, isn't it? As a function of lambda. Yeah, it's strictly increasing. Huh? E to power lambda. So now, if I were to draw, let's say, a line such as this, slope lambda, so then lambda x minus this function, right? So I'm trying to find a point lambda x minus. This is where lambda x. No. Yeah. So this is where lambda x is minus x is positive. So maybe around somewhere around here you get your. So suppose the slope is x, this is lambda, and at this point, I guess this gap is maximized. So that's your lambda star x. And now you can ask me, if I change my slope, what does my lambda star x do? That's a picture to keep in mind.
Is it different from
What's that?
Is it different from microfinance?
It's the same, I guess. I of x we had earlier defined as infimum of s nu mu and showed it to be equal to this. No, it's the same. It's the same. It's just I of x we use for general rate functions, and in the ID setting we're going to call it lambda star x. Just to highlight the fact that it's kind of conjugate of lambda. It's related to lambda functions. It's a notation that's become standard. So we'll have so Sn is summation xi I equal to 1 to n. Xi has distribution mu. Sn by n has distribution. We call it mu n. These are all the distribution induced on the real lambda. That's what it's called. So Kabir's theorem now is So this files. The largest principal. Convex equation. So where it will be convex. All G, but it's divided out R. Same old stuff. I think it's exactly the same stuff. Except I'm calling it I for some reason. And then just have- Okay, so first some things. So lambda is convex. So I showed this earlier by arguing that its double derivative is strictly positive. But that's only true at the region where the double derivative exists. So I've talked about when the double derivative exists and all that. So I didn't do all that last time. This is that's it. But a more straightforward way of seeing its convex is just from using Holder's inequality. So how we show something is convex, we show lambda theta lambda 1 plus 1 minus theta equal to is less than equal to theta. Right, that's what this actually means. Now this guy here is expected value of log of e to the power theta lambda 1 plus 1 minus theta lambda 2 x. This is powerful, huh? It's kind of nice for also that can be this e to the power lambda 1 x to the power theta to the power 2x to the power 1. And now I just this is my x, this is y, and I apply holders to it. So I guess this is so what I'm going to do. Theta is basically 1 upon p. So I'll upper bound this by raising it to the power p. So raising it to the power 1 by theta. So this should follow lambda 1 x to the power theta theta bar lambda 2x. Let's see why this is true. The folder is theta bar. Assume it's non-negative. One by two, right? 1 by p plus 1 by q. So 1 by p is my theta.
And that will be
So y is
E bar lambda 1 is theta.
yeah, e to the lambda 1 x theta is by y. Okay. So then I multiply, I raise it about 1 by theta, and outside I put theta. So same thing here. Okay, now if you just simplify, so this is a inequality here, and this is just theta times it's 1 minus theta. Good. So in this, all I've done is I looked at this thing basically. All the lambda, so this I would call as domain of big lambda. Let's put all lambda. So I take lambda 1 and lambda 2 in this domain, and this follows. So I get convexity in the complete domain. Basically. Both these terms are finite, so nothing to worry about. Okay. Now to show, so let's also define the lambda star x such that lambda star x is less than infinity. So we want to show that lambda star is convex. So again, we look at lambda star theta x1 plus 1 minus theta x2. And by definition, so over lambda, right? Theta x1 plus 1 minus theta x2 into lambda. Okay, so how do we proceed from here? What do we want to show? We want to show that it is equal to theta times sup lambda x1 plus 1 minus theta times sup. That's what we want to show, right? And this I can just write here as theta plus 1 minus theta. Now it's possible. Because this, let's assume for now that these sups are actually achieved. If they're not achieved, then you get arbitrarily close and all that. But let's ignore that. If that's achieved at some point, then that point is one of the candidates here, and that point is one of the candidates here. So these will certainly dominate that. Yes. Very natural kind of definitions. Other thing to show, this is interesting. That so I'm going to assume. By the way, that Kramer's theorem which I showed you above, I didn't assume anything about the distributions. It was always true. So that's pretty fantastic. It's proving great generality. So whether the distributions have mean or not, whether they're fat tail, light tail, it's always true. For every set, every Borel set G. It's quite nice that one can write things in that generality that simply. Okay. What else do I want to show? Yeah. I guess one should also argue that lambda star x, the way we defined it, for it to be a rate function, for this guy to be a rate function, first of all, it has to be non-negative. So, is it clear that this is non-negative? Take lambda to be 0, right? This guy is 0, by the way. When you log more range function is 0. Other thing you want to show is lower semi-continuous. And one definition of function being lower semi-continuous is that if xn goes to x, then limit fxn greater than equal to fx. You can see that this corresponds to the definition of level sets being closed. So the picture is as follows. So continuous functions are of course lower semi-continuous, because in that case lim is equal to lim, and this is equal to this f of x. But so if you have a gap here, you can jump downwards. That's allowed for lower semi-continuity. So f of x is less than or equal to lim of f of xn from both sides. Okay. Right. But I can't have this going upwards. And you can see that level set in that case will not be closed if there was upwards. But if it was downward, then the level set. So it's a small exercise to see that this and that definition are the same thing. That you may have already done somewhere. But this kind of makes sense. I don't have good examples right now where this will not come up in large deviation theory. That you'll have a picture like this. At least I can't imagine one right now. Yes. I mean, these things happen a lot. I guess you could probably have. Like,
You're saying the illustrator is fully continuous?
no, it's load semi-continuous, right?
No, you said this cannot happen.
No, in the sense I can't think of random variable x size, so that the rate function has its jump downwards, and everywhere that it's higher. At one point it's downwards. It's hard to. It probably doesn't exist. But there are other cases where you have discontinuity, but lower semi-continuity. One is of course you just jump upwards and then.
Can't we take in some random variables which is goes to Dirac delta distribution?
Say again?
Towards a Dirac delta distribution?
Your voice is not so. It's very mild. You have to speak up.
I'm saying that towards any Dirac delta distribution.
Towards Dirac distribution, yeah. No, so okay. So suppose you have something which has very little variance, right? Very little wiggly, and now you're taking the average of these things. So that will also, it just put a mass on the support, and then it'll be infinite. It can't take any value large. The rate function will be infinity outside the support. But you won't get this dip downwards on one point. Actually, your point is suppose you just okay. So his point is actually a good one. Let's have a degenerate case. each xi is equal to 3. Then of course you have okay plus infinity up till 3. At 3 you have 1 and then you have plus infinity everywhere else. So were you thinking of that or you could be thinking about that I guess?
Yeah, kind of, but where Dirac delta mass was stated at point,
Yeah.
get the term.
So exactly, it is a Dirac function, it's just total mass at one point. Then you get that. Yeah. That's a good example. I was kind of thinking that okay, I'll have a nice picture and then you come down, go down, come back up. That I don't have. Because probably that doesn't exist, but I've not thought about it. Okay, so yeah, so why is this guy lower semi-continuous? So you can see that, okay, let's look at lambda star xn that's equal to. So
Each level set is an intersection of closed sets. For each lambda, you have a closed set. As this lambda is minus delta and this equals to b. You are taking the intersection over all.
Yeah, so the question we're asking is why is this level continuous? And your point is that this is supremum of all these kind of functions.
So each level set is the intersection of over each lambda that lambda x minus delta lambda this and equals to.
Yeah.
That is a closed set.
Right.
It's an intersection of those.
Yes, once again. So lambda, okay, so this is. So is it clear that lower semi-continuity follows that way? Or?
Yes, so
Big lambda is continuous, right?
Yeah, big lambda present.
yeah, so the level set is
Hmm.
the condition is for all lambda we need lambda x minus lambda
So
lambda x.
yeah, that's right. So that's what you're saying. All we need is lambda. So basically, for all lambda,
For all lambda in R, lambda x minus lambda lambda x
that's then equal to alpha.
Alpha. And
Yeah.
so this
For all lambda.
yeah, so the level set is the intersection of
Okay,
these
because it's exactly close sets, it's close. Yeah, sure. Okay. Of course, yeah, straightforward. Yeah. I just had up the proof in mind from the book, so I was going to think of this is actually correct. Okay, good. Okay, so this is fine. One example of when this is not a good rate function is suppose your d lambda is equal to 0.
what is D?
This is the domain of finiteness of log Moivre function. So you can have a distribution so that Moivre function for any lambda plus or minus is infinite. Polynomial pairs on both sides, for example. Take it. Now you can see that okay, so this guy is going to be infinite for all lambda except for lambda equal to 0. Right? So then the lambda star x is going to be equal to identity 0, right? For all x. That means a flat curve. So it's so all the level sets are closed, but they're not good level sets. They're not compact. Good rate function, compact level sets. Yeah. So this is an example. So you could have cases where you have a rate function is not a sticky convex function, and and it's on a good rate. Okay. Okay, suppose now, so I'm going to assume that the mean E of x exists, it's finite. Okay, let's assume that. So now for x greater than E of x, then equal to E of x. Before that,
Exists, which random variable is it?
no, so Sn by n is Sn is sum of id variables. So mean of the each increment xi.
Okay,
That's it.
exists.
It's finite.
No, what was x?
What else?
What was x?
Sn equal to summation xi. Right?
Yeah, so each of
Each of the IID.
each variable.
Yeah, each the IID, then the mean is finite. So let's assume that's the case. Then, so what can we say about lambda star? Basically, let's just go back to log of e to the power lambda x. Let's equal to lambda.
E of log.
What's the right? E of, I guess, lambda into E of x, right? By we can, yeah, if we take a log inside, we get a lower bound. Okay. For all lambda. So that is okay. Lambda times E of x minus lambda lambda. Oh, less than equal to 0.
Yeah.
Then same is true for supremum.
0.
So yeah, so that is it. And the start equals 0. This is useful. This will help with the other properties which quite nice. For x greater than E of x, lambda star x is supremum lambda non-negative lambda x. What I'm saying is you don't have to consider non-positive lambdas. What's that?
For that system.
That's right. Yeah. This is because let's take lambda to be less than 0. Then lambda is into x is greater than ex, right? And x minus ex is negative. That tells you that lambda x minus lambda. So now I can take soup over all lambda non-positive, and that's going to be less than equal to soup of all lambda non-positive here. That's less than equal to 0. So this is going to be less than equal. So I can ignore this. So I can just limit myself to that guy there. Same argument will work in the other direction. Yeah. So for x less than or equal to E of x, lambda star lambda is equal to. So these are just some preliminaries that we need to know. Okay. So other thing is which is interesting is as follows. This is good to see if you've not seen this earlier. let's look at lambda log of equal lambda x with lambda lying in interior of the domain of finiteness. So there was a neighborhood around this lambda where your log homogenic function remains finite. Okay? We have to say yes. So lambda is in that case lambda by lambda is equal to, so it's differentiable in the interior of its domain of finiteness, and lambda prime lambda is equal to all the things you are assuming you're showing now. X1 e to the power lambda x minus. Yes. So point is, let's not assume this, let's show this. It's true in the interior of the domain. So how do we show something like this? That's right. So basically, we look at log of, I guess to show that this is differentiable, it suffices to show that its exponential is differentiable, right? This composition of a smooth function is going to be continuous. So I'll just look at expected value of e to the power lambda plus epsilon x minus e to the power lambda x divided by epsilon. Limit as epsilon goes to 0. And the argument is going to be that I can interchange the limit expectation. So once I bring it inside, then of course I get x. So I need to dominate this guy. So one can argue, and this you can show with calculus. Power lambda. This is just we have e to the power epsilon x minus 1 upon epsilon. Right, I can rewrite this one. And let me just ignore this for a moment. This guy I can dominate by e to the power delta absolute x minus 1 upon delta for some delta. So because I'm in an open set in my domain of finiteness, I can find some delta, and for all epsilon less than equal delta, I get this property. And now this is going to be integrable. I'm going to have e to the power lambda x here, e to the power lambda x here. Okay. This is integrable, and this dominates this guy for all epsilon going to 0. So I can use dominate. Okay, so all that is good. So we can use this argument to show that this log homogenic function in the domain of finiteness, in the interior of that, it's infinitely differentiable. So that's a homework problem for you. At some point. This is nice. And now, so again, I have lambda star x is equal to soup. So suppose there exists data such that lambda prime data is equal to x. Okay. That would imply that lambda star x equal to eta into x minus lambda. Same thing we just said earlier. This is a nice concave function, which is differentiable. Now we know it's differentiable. Okay. So if we can find a point where the derivative is 0, then that is 0. So this will be useful to us. Now let's go ahead and with this diagram, let's go ahead and try and do the converse theorem. Right. The first thing I'll prove is that mu n x to infinity of sigma Sn by n is equal to x. Okay, so consider this. Okay, so this is what we're going to show right now. And this is basically, the what we do with Chernoff analysis and all. How do we proceed here? Well, you have to show this.
So it's straight
Huh?
So the expectation of this is equals to probability exp of E Sn by n greater than equals to exp of T x person.
This is Sn getting to nx. So it's- This you agree, right? Sn by n is greater than equal to nx. Alright. Now this becomes equal to e to the power minus theta nx and e to the power theta Sn. This is IID, right? So you get e to the power n times lambda theta e to the power minus n and then you have theta x minus lambda theta. Now what do I do?
Set theta to be the one which attaches supreme.
Sure. Or since this x is going to be, for this to be sensible, this x has to be greater than e of x, right? Greater than equal to, let's say, e of x. Otherwise, it's converging to 1. So let's take x to be strictly greater than e of x. Let's take it to be greater than e of x. Take it. Now, whatever I did was true for theta, but non-negative. So I just take this to be. It's true for every one of those theta, so I can ignore myself. Supremum over theta. Theta x minus lambda. And we know that this is the rate function, right? That's lambda star x. Right, this was true for theta non-negative. It was not true for theta negative. You agree with it, right? So now I can just, it's true for every theta. So I just take the infimum outside, it's true for the infimum as well. And that corresponds to supremum here. And that gives me my n lambda star x. Okay. So exactly the same argument.
Now there should be a corresponding work on.
Yeah. But we want to prove these things with general Borel sets. So we're going to go. We're going to go. We will tackle this problem in more generality. But so let's complete the upper bound first. So we just done this for one set. Now similarly, I can get probability of Sn by n less than or equal to x. When x is equal to e of x, I'll be able to show that this probabilities are basically order 1 quantity, so that it's e to the power minus n 0. Just follow the lambda star x will just become equal to 0 in that case. But and then you can show exactly the same way. Now I'll do exponentiation. I'll take theta to be negative, so I get e to the power minus n lambda star x. ठीक है
And the corresponding upper bound. I mean, there should be corresponding lower bound.
yes, lower bound. Let's complete the upper bound first.
Yeah.
Right now, what I want to show is that if I give you a set G, then we call it set G is closed. I just want to show that okay, lim soup 1 by n mu n G, log mu n log is less than or equal to minus infimum lambda star x. X is in G. I want to show this first of all. Then my upper bound will be complete. There are good lower bounds. I mean, all of this is given in the book, but I still want to do it slowly once because some of the things are very cool the way they are done. So it's good for you to see them. It's still easier that we do it here rather than when you read on your own. Makes reading it so much more easier. Okay, so what do we do here? So first of all, let's assume that let's call this I of G. Infimum and let's start x. X is in G. Okay. So I'll assume that okay, I of G is greater than 0. If I of G is equal to 0, then there's nothing to do. This is always true. If I have 0 here, it's always true. This probability is mu and G is less than or equal to 1. Okay, so let's assume I of G is greater than 0. That means E of x is not in G.
Not
If E of x was in G, then this would have been 0. So that means, yeah, so E of x is here. So I can look at all the open intervals which are not in G and take their union. All the open intervals which contain E of x and which are not in G and take their union. Suppose the union is x1, x2. Okay. Now, both of them cannot, it cannot be that x1 is minus infinity and x2 is plus infinity, because then G would be empty. I'm assuming G is not empty. It could be that both x1 and x2 are finite. That can happen. Because G is arbitrary, it's an arbitrary closed set. But suppose x2 is less than infinity. Then x2 is in G. Because it's a closed set, right? G, yeah. The union will have to touch it. Which tells me that okay, lambda star x2 is greater than or equal to I of G. G is the infimum of all x in G. Right? Similarly, okay, I can say that if x1 is greater than minus infinity, then x1 is in G, and lambda star x1 is greater than or equal to I of G. So in particular, mu n of G is less than or equal to mu n of x2 to infinity plus mu n of minus infinity to x2. If x2 is infinity, then this is just a backward statement. If x1 is infinity, minus infinity, it's a backward statement. Both of these I can upper bound by 2 times e power minus n I of G. So I get my upper, now I get my upper bound. So log of this is log of this quantity, and I divide by n. I get this minus I of G as upper bound. Okay, so this is what I want to do. So yeah, this is for you to see key. Essentially, half lines was enough. Once I had that, I had enough for general sets. So not too much has been gained by doing these things in generality. Because again, how does the rain event happen? How does probability that Sn by n is in G? G is a closed set. This is the P of x here. So either there's some point x2 here or there's some point x1 here. So it happens the most likely way. This will either be equal to x2 or will be equal to x1.
One of these lambdas will contribute.
Yeah.
One of these elements in G.
I mean, you could have a set where both of these are equal. So that's the only issue.
Yeah.
They're equally rare.
Yes. At most two of the elements in G will contribute to most of
That's
the probability.
That's it. Yeah, so it happens the most likely way. That's the key intuition. Everything else is just kind of, making it look fancy. But the making it look fancy is so nicely generalizable that it has a lot of value. Okay, so now we got the upper bound, now we already got the lower bound. So lower bound boundary in time, I want you to say some quick ideas.
The limit will be at least the minus of all G in the interior I.
Sorry?
So limit you are saying so the corresponding lower should be limit of this thing is created equals to minus of all x in interior of G.
That's right. Yeah, that's right. So limit of 1 by n log of mu and G is equal to minus infimum of
X in interior.
infimum G.
So particularly G is open, this means the limit always exists.
If G is open, no, the limit may not, because the limit can still differ from lim soup, right?
But you're saying the limit is lower bounded by something. And then the lim soup is upper bounded by the same thing. If G is.
No, that's if your lambda star x is continuous.
Oh.
It has the same value as infimum over G naught and G bar.
No, G is open.
Okay, G is open, yeah.
Towards but no.
Yeah, but then
Yeah.
you're not saying anything.
If lambda bar is continuous, then
Yeah. That's it. So you need the continuity of sets of continuity of lambda star. But the point is here, let's look at a point x which lies in the interior of G naught.
we will simply find the probability that mu n of G equals to x.
Well, no, so there is something more than that. So then this tells you there's a neighborhood around it which is also in G naught. So I can then show that okay, lim inf n goes to infinity 1 by n log mu and G is certainly greater than equal to lim inf n goes to infinity 1 by n log mu n of, let me just use some loose notation, x plus delta. This will be your view, right? Because x minus delta, x plus delta is in G naught. Okay. If I can show to you that this is getting equal to minus lambda star x, my claim is done.
Yes.
Okay. Because now G is fixed. I'll just take an infimum over all lambda star x in G naught. So all I really need to do is just show you this one. Okay, that's all I need to do. Roll one is follow. My claim is here also all I really need to do is show you this part. We assume that 0 lies in. Let me assume it. Just kind of normalizing things. See, lambda star 0 is nothing but negative of minus infimum of this one definition. So if I just show you this will suffice. This implies that basically. And so why is that the case? Yeah. So, if above follows for x, then this follows for x minus x. Let me just say this for example, that time is limited. So next time I'll go through this more slowly. But the point is, this will suffice to show that. Because if you show this, then just by scaling, by translating, you can show that. And how do I show this? So this is all I need to show. So I just get the big idea here. So I need to, I'm looking at this guy here. Right? So I want to show that this is equal to some lambda A. This minimum exists. Now, it's a convex function. There could be funny convex functions like this, etc. Right? They could have multiple minima and all that kind of stuff. That's always a problem. Yeah, even if it's non-decreasing, I can always have these problems. So what I do is, did I say lambda was non-decreasing? I should have said that. X takes negative as well as positive values. Yeah. So I shouldn't have said that. It's just an arbitrary general function. Yes, that
If x is greater than equal to 0, then it is If x is greater than equal to 0,
then it's more. Yeah, only then it's more.
Yeah.
And if it's x is less than equal to 0, then also it's more than Yes, yeah. So that's what I could have said. But I don't think I needed monotonicity whenever that came up earlier. Just continue to go. So what I'll do is I'll assume that my random variable is bounded. Okay. And further I'll assume that mu of minus infinity to 0 is greater than 0 and mu of 0 to plus infinity is greater than 0. What this does is, at the very least, it tells you that lambda goes to infinity as just go back to the definition. Log of e to the power lambda x. When this goes to plus infinity, the small values like don't matter. And then their contribution is become tiny. But whenever, if this is taking positive values with positive probability, then that will take this to plus infinity. That will take the whole thing to plus infinity. Same argument in the other direction. So then you have a nice function which is nice and continuous, and it's finite because it's bounded random variable. This is always for every lambda this is bounded over. So it's a bounded random variable, finite, and it's essentially like this, strictly convex. So this eta will exist where this derivative is 0. Okay. So lambda prime eta is equal to. So that's what makes my life easy. So let me just show this, at least for that random variable. So now this eta is given to me. What I'll do is, how are we doing in time? How badly are we doing on time? I'll just take 1 second. So what I'll do is I'll look at this probability. Probably with Sn by n divided minus epsilon. Sn by n need not be 0. This is a rare event, right? And this is going to be equal to mu1, mu x1, mu xn dx let's say this is for it d mu x or d mu xn. Summation xi I equal to 1 to n. In absolute values that's equal to n, right? So what I'll do is, because that data exists, I look at a new change of measure, d mu star by d mu equal to e to the power eta at x e to the power x minus lambda. So this is how I define my new measure. What that means is, technically what this means is that mu star of A is equal to E mu of e to the power eta x minus lambda eta. That's all. This is a Rayleigh-Nicolin derivative which exists now. This eta is given to me. So I'll define new measure in this manner. It's a proper measure because it's non-negative and it integrates to 1. Okay. With this measure, I'll re-express this as e power minus eta summation xi equal to 1 to n plus n times lambda eta into d mu tilde x1 d mu tilde x. Summation xi. The point is, this summation xi is at most n epsilon, right? So I get a lower bound on this, which is e to the power minus absolute value eta into n epsilon from here plus n lambda eta. And then I get the probability of this change of measure that Sn by n lies in minus epsilon. Now my change of measure is such, because lambda prime eta is equal to 0, the mean of each xi is 0 under this change of measure. So this probability is actually not a small probability. It's converging to 1. So now when I take a log of this probability of Sn by n minus epsilon plus x, when I take a log of this and divide by n, something which is going to 1, I take a log of that, this is going to go to 0. That's a good thing. This vanishes, this gives me lambda eta, this gives me something which depends on epsilon, but epsilon is arbitrary. So I get lambda eta, which is what I wanted. So that's a key argument, and then we'll put all kinds of bells and whistles around it. But when I started talking about large deviation, I said basically boils down to change of measure. Then you change your measure the right way, you make that event more likely. So that's kind of captured from here. Okay, guys. So we'll meet next Friday. Okay. All right. Any questions? Saurabh, Malhar. I think they left long time ago. Okay. Right. Okay, whether you're here or not, let's see where next Friday.